I hope this will make some of you very happy, because at last we'll be able to use the rules of differentiation, and so very soon you will be very soon applying these rules, and you can forget about the differentiating by definition, except for the first midterm, where you'll be asked to find the derivative of a function, at least for one problem, by using the definition. Okay, but after that, you can apply probably rules that you learned in high school from then on, and so I guess this is good news for some. So rules again. Now that we're looking at the derivatives of functions at just any point, and we're looking at so we're viewing now derivatives as functions themselves. So the first rule is that the derivative of x is just 1. The second one is that the derivative of any constant is equal to 0. And I guess those, are not problematic at all to apply. The third one, I wanted to stop a little to make sure that we are not going to miss any points in the exam or in the quiz. Then this is the very important power rule. That says that the derivative of x to the alpha is equal to alpha times x to the alpha minus 1. Here alpha is not necessarily a natural number, but a real number. And so that's why I wanted to make a few comments and give some examples. For instance, if I compute the derivative of x to the, say, some number like square root 2, we apply the power rule. Here alpha is the square root of 2, and so we should get alpha, which is square root of 2, times x times the square root of 2 minus 1, right? So that's first example. Second example, or I can just write it over here since that didn't take much space, is that we can apply it to things like 1 over x to some power, like x cubed, for instance. The only difficulty, if any, probably some of you are very comfortable with dealing with inverses of power functions. First, we write this, what's inside the parenthesis, as x to some power. Since we're writing 1 over x to the cube, we must write x to the minus 3. But once we do that, then alpha is, we already found that alpha is minus 3, so we apply the rule blindly, which tells us that this is going to be equal to alpha, which is minus 3 times x to the minus 3 minus 1. So alpha is minus 3, so this is alpha, and so this becomes minus 3, x to the, minus 3 minus 1, that becomes minus 4. This is not minus 2. Some people may get confused and add 1. You're always subtracting 1. You see, it's a negative number, it becomes more negative. And we can, if you want, so we can write this as minus 3 over x to the power of 4. Now, some other things that may happen is that you may be asked to find the derivative of, say, the square root of x. Again, the thing is always about finding what alpha is. And when you have the square root, remember that that's the same as raising x to the power 1/2, x to the 1/2. And then, now that we know that alpha is 1 over 2, 1/2, Let's apply the rule. 1/2 x to the 1/2 minus 1. 1/2 minus 1 is in the exponent. That, if you do the simple arithmetic, becomes minus 1/2. Or we get 1 over 2 times x to the minus 1/2. Since that is a negative power, we may write it as 1 over 2 times 1 over x to the 1/2. But x to the 1/2 is just the square root of x, so we may write this as 1 over 2 times the square root of x. Okay, and so there are combinations of these things. So in example, you may be asked to differentiate the fifth root of x squared, say, or x cubed, or say x to the 4th. Use a different number. And again, we must identify alpha. Alpha, which in this case is equal to, what is it equal to? 4 over 5. Remember that what's in here on the root becomes a 1 over, in this case 5. It's only in the case of the square root that we don't actually write a 2 over here, but for all the other roots we write a small number outside the root sign. So this is equal to x to the power of 4 over 5. And again, the rule tells us that that's 4 over 5, x to the 4 over 5 minus 1. But then the exponent becomes minus 1 over 5. Four over 5 times x to the minus 1 over 5. But this is a negative power, so this becomes 1 over x to the 1 over 5. If you want to simplify things even more, this becomes 4 over 5 times the fifth root of, not to confuse it with this 5, fifth root of x. So this is actually something I may ask for Thursday's mini quiz. So the only thing to pay attention to when applying the power rule is that you need to identify what alpha is. And that's all. So, I mean, in some cases it's evident when you write, say, x to the 4, alpha is 4. But when you use some roots and combinations of power functions and such, or negative powers, you need to be careful not to get confused and find the right power involved. Now, a fifth example, which is really a non-example, is something that is a very common mistake you need to avoid. So the power rule doesn't apply to expressions like 3 to the x. A very easy way to remember this. So this is the mistake. People are asked to differentiate this, and they write x times 3 to the x minus 1. Okay, so this is completely wrong. This is incorrect. Power rule applies to to expressions of the form x to some constant, not a constant to the x. This is something I may also ask for the mini quiz. So it applies whenever the variable is not in the exponent, and the exponent is a constant. That's where it applies. So you have some constant raised to a variable exponent, then the power rule does not apply. So don't ever do that. That's going to be wrong. Okay, so pay attention to this. Now, one of the other things we're going to give with, which is not really expected of you to know how to derive at any point, because it relies on a limit that we are not going to prove. It requires higher math. I'm sorry. So that's the limit. We need to know that the limit, the following limit, we need the limit to know as h approaches 0 if e to the h minus 1 over h is equal to 1. So the exponential function, the derivative of e to the x, is then derived as follows. Remember one of the definitions, the second definition, the one involving h going to 0, tells us that the derivative of e to the x would be, at the point x, would be e to the x plus h, where that's f evaluated x plus h, minus e to the x, which is f of x, all of that divided by h. So then, this is the limit when h approaches 0 of e to the x, but there's a property here of exponential functions. Whenever you're adding something in the exponent, it becomes a product like this. So e to the x times e to the h, and then minus e to the x, all that divided by h. Then we have a factor of e to the x, a common factor we can bring out. E to the x times, and we have e to the h minus 1, all that divided by h. But here notice that e to the x does not depend on the variable here h. So we can bring it outside of the limit. E to the x is constant with respect to h. It does not change when h changes. So we may write, this is e to the x times the limit of e to the h minus 1 over h. But wait, this limit here is the one we just assumed to be equal to 1. And so that requires course in analysis to prove. In fact, the number e is defined so that this limit is equal to 1. So it's kind of cheating. But for us, I mean, we'll just assume that this limit is equal to 1. And with that at hand, we can conclude that the limit here, or that defines the derivative of e to the x, gives us e to the x. So the derivative of e to the x is e to the x itself. Now, the important thing about after all of this is that we can combine known derivatives. After a while, we'll be able to compute derivatives of sines and cosines using the trigonometric limits we saw last week. And we'll derive a rule for the inverse function, and then that will allow us to compute the derivatives of arcsine, arccosine, and also logarithm, which is the inverse of e to the x. We'll derive a rule for products, and finally a rule for composite functions, but that's way ahead. We'll get there. But for now, what we know so far, we can easily compute derivatives of the sum of two functions or the difference. This is just combining what we have so far, and we may apply this very easily. So whenever you want to compute the derivative of the sum of two functions, just compute the derivatives of each function and then add them together. So for example, we can combine what we've just gone over and compute we may be asked to compute the derivative of, say, e to the x minus x squared plus 1 over x and plus the cube root of x. Okay, this tells us that we can take the derivative of each expression separately and add everything together. When we have minus sign here, it's minus, so we get d dx of x squared, then plus the derivative of 1 over x, and then plus the derivative of the cube root of x. The derivative of e to the x is e to the x, we just saw that. Using the power rule, we can find out that this is 2x to the 2 minus 1, which is just 1, so minus 2x. Again, by the power rule, what is exponent here? This is x to the minus 1, so when we apply the power rule, we get minus 1 times x to the minus 2, so it's going to be 1 over x squared, and then plus the derivative here. What is alpha? Again, the power rule. Alpha here is 1 over 3, so we get 1 over 3 x to the 1/3 minus 1. And this is equal to e to the x minus 2x minus, you have a plus and minus here, minus 1 over x squared plus 1 over 3. X to the 1/3 minus 1 is just x to the minus 2/3. I mean, you can simplify this expression further, but this is going to be enough for me, at least when I'm grading the exam. Now, the constant multiple rule is very simple. So it tells you that if you have a constant times a function and you differentiate, you just differentiate the function and multiply that by the constant. This is a very quick example. The derivative of, say, 5 times e to the x is equal to 5 times the derivative of e to the x, which is just equal to 5 e to the x. Because 5 is a constant, and we may replace this by any other number. Pi is a number, so we may apply that as well, right? And that sums up all rules that we need to know. In next week, we'll go over the product and quotient rule, which will complete all the material for the exam, and we'll see some some first some information that we can draw from the derivative, which will tell us something about the function f. Later on, we'll see what the second derivative, which we haven't talked about, is going to tell us about the function. Specifically, I mean, going back to the derivative, the sign of the derivative will tell us the whether f is increasing or decreasing. Remember, the f prime is the slope of the tangent line. So if the slope is positive, it means that the function is going up, so it's increasing. When it's negative, it tells us that the function is going down. And we'll be able to draw some rough information about f based on the knowledge of the sign of f prime. I'm sorry. First thing to notice again is, for instance, remember that we discussed the equation of the tangent line. So going back to the tangent line, and we'll conclude this with this observation here. So what's special about this point, this point, this point, and this point? So here the tangent line is given by something like that. So at this point, say A1, and it's some oblique line going upwards. But here at this point, say A2, and the same is going to be true at A3, A4, and A5. The tangent line is horizontal. And horizontal simply means f prime is equal to 0 at that point. Tangent at point A. So the point A, if the derivative is 0, you speak that when you say that there's a horizontal tangent line. And that's all that is. So let me see if I'm forgetting anything. So horizontal tangent, yeah, it's just this. So whenever the f prime is equal to 0. So you may be asked, say, now we can combine everything that we've done so far, and you may be asked to find the points where f of x equals x cubed minus 1, minus x has horizontal tangent. Again, this simply means that we need to find the points such that f prime of x is equal to 0. What is f prime of x? Again, the power rule and the rule for the sum and difference of functions. So this is the same as, well, root of x cubed minus x prime, or x cubed prime minus x prime, and this is just equal to 3x squared minus 1. And so setting this equal to 0 gives us that x has to be equal to plus or minus the square root of, I'm sorry about that, 1 over 3, the square root of that. I don't know why it's so ugly. Okay, so that's the thing. So those are the points where f of x cubed minus x has a horizontal tangent. See, now we've been able to combine everything in one single problem, and we'll continue next week with the sort of, as I said, with the sort of graphical information or qualitative information we can draw about f from knowledge of the sign of the derivative. We'll see what it means. I mean, what can you see? I mean, just by looking at a graph where a function is differentiable or not. And finally, we'll go over the product and quotient rules. And that will be it for the exam.